Hi everyone, very pleased to see you there. For those who don't know me, I'm Simon Robert. I'm the R&D manager in Sixense at the Geophysics department. For this presentation, I will be joined by my dear colleague Maria Saadeh. She will present herself later. This presentation will be divided in three parts. First part, a short presentation by myself about our group, Sixense, and the main focus of this talk, why we decide to do this webinar. It will last approximately 5 minutes. And next, the stage will be for Maya for the main topic of this talk, the focus on passive seismic methods in applied geophysics. We will give you what we know, the main methods, their advantage, their limitation, and our vision about this kind of survey. So, in the last session, as I said just before, it will be a Q&A session. So right now you can ask any question in the chat, and during the presentation of Maya, I will manage the question, and we try to for the Q&A session to answer a maximum of questions. Okay, so first, my presentation, does it work? 2 seconds, sorry. Okay, so our group, it will be very short. You will see only 3 or 4 slides. It will be very short. Maybe you don't know, Sixense is a subsidiary of Vinci Group. For those who don't know Vinci is a major player in 3 main domains, energies, construction, and concessions. Sixense is what we call a specialty businesses of Vinci Construction. I'm going to try to explain you why just after. So, here you have a map about all our offices in the world. The main spot globally in France, UK, Hong Kong, Australia, North America, and UAE. Also you have the main figure at the bottom part. I won't comment this. It's not the topic of this talk. Our mission, as we define our mission at Sixense, we help our client to face the challenge of construction market and asset management. For this, we retain 4 main issues: the aging of infrastructure, the land use density, the environmental issues, and the digital transformation. This webinar is situated in the main issues of land use density, evidently. And how we are organized to answer this. We have 4 areas of expertise: engineering, monitoring, mapping, platform solutions, and at the right you can see our fields of interventions. Just to give you an idea, the Geophysics department is located in the engineering part. So I think it's enough for a presentation of the group. Now we will focus on why we decide to do this webinar. It's really simple. Most of you know classic geophysics seismic methods like MASW, refraction, boreal tomography. They are very useful in applied geophysics, but they have some limitation, clearly, notably in noisy area, and they need to have a geometric array. So here the big change is coming with the passive seismic methods, because you have an easy access, sorry, to a 3D model. You don't have to have you don't need to have a geometric array, and you can cover a large area. So but we can consider passive seismic like a recent evolution of our job. The theory of passive seismic is not very recent. We talk about this in academic research since the beginning of the 70s. But the real application in applied geophysics, we can say it's only since 3 to 5 years. We use it regularly. And it's normal because passive seismic survey needs a lot of equipment and expensive equipment like nodes, like cable system with a huge capacity of storage, and you need a lot of informatic resources, notably to manage all this data. Just to give you an idea, seismic interferometry acquisition. It's around 1 terabyte of data, so you need a lot of resources to manage this and to process this. So here we are here to explain you the different methods of passive seismic. How we can start with only noisy waveform between two detectors and to obtain a 3D model. And for this, we will try to give you our vision of the new passive seismic methods and in which application they are better. So for this, right now, I will leave the stage to Maria, and don't hesitate once again to ask your question in the chat, and I will see you at the end of the presentation of Maria. Maria.
Okay, hi everyone. Thank you for your presence. Thank you for being here. So my name is Maria Saadeh. I'm a doctor in seismology, and I'm specialized in seismic interferometry and passive monitoring. At Sixense, I use my expertise to evaluate seismic methods, and I work mainly on the data mining related to passive tomography by seismic interferometry, or what we call at Sixense the Sissterra methods. Okay, so what is this talk about? So we are often asked, what is seismic noise, how it is used in seismology, and how do we extract waves from it? And people sometimes confuse the different passive methods. So we are here today to present to you from our humble experience the basics on seismic noise, the most common methods that use noise as a signal in applied geophysics, and the main differences between these different methods. So let's start with the basics. So what is seismic noise? To answer this question, we'll start by showing the different type of seismic signals here on this general frequency spectrum. And as you know, the lower the frequency, so the higher the period, the deeper the wave propagates. So on the spectrum, we see signals that are emitted by earthquakes, by active sources such as earthquakes. So an earthquake signal can propagate deep in the earth, so could have a large frequency range. We could see also on the spectrum smaller scale active sources such as hammer or any type of small scale source that could happen on the surface. These sources are present at higher frequency with a signal that propagates in the shallower layers. So active sources are characterized by a defined source location and time, and they emit ballistic waves, as we see here, that can be easily detected on seismogram. But on the spectrum, we see also a seismic noise that have different sources at different frequencies. So we have, for example, the hum of the earth at low frequency, so high period, which is the continuous free oscillation of the earth. We see also what we call microseismic noise, represented by two peaks here, and it's emitted by ocean waves and their interactions mainly with the seafloor. And another seismic noise present at higher frequencies is human activity, such as traffic, industrial work, but also atmospheric sources, rivers, etc. So this noise is also a source of waves that propagate through the earth. Now, the characteristics of seismic noise is that its location is not defined, not like active sources, because the locations are multiple and it's a continuous signal. So it's present everywhere all the time. But using advanced mathematical procedures, the waves hidden in the seismic noise could be extracted and analyzed. When it comes to applied geophysics, we are interested in analyzing the shallow crust. So we work with periods lower than 1 second. And we need waves. So we need a signal to measure and to analyze. So we usually induce active sources in order to emit a signal, record it, and analyze it. So active sources could be various, as we see here, depending on their amplitude, the area of study, etc. It could be a hammer for small-scale studies, for example, a weight drop, an explosion for large-scale studies, etc. However, the passive seismic noise is present also everywhere, all the time, and it could be emitted by anything that happens on the surface, as we see a few examples here, traffic, trains, construction sites, etc. Okay, so this seismic noise exists, but how can we use it and why would we? What are the advantages of using this noise? So actually, around the 20th century, we were able to record ambient noise signal for the first time and analyze it. And we understood that noise, seismic noise, is also waves that travel through the Earth, and it's dominated by surface waves since its sources are mainly surface processes. And with mathematical processes, these waves can be extracted and we could analyze them. As we see here in this image, we're going to talk later a bit more about the cross-correlation procedure. Also, using seismic noise can be sometimes the only solution, especially when it comes to urban areas where the use of active sources is not recommended. And another big advantage of using noise is that we do not need to take care of the characteristics of the active source, such as its location, its type, its amplitude, etc. And that is actually a big relief because active source characteristics should be well defined for each study. And in some cases, they could be not well adapted and could be a constraint. So there are also other advantages of using passive ambient noise, and they depend on the methods. We're gonna cite a few of them later on. If you're familiar with any passive seismic method, please go ahead and cite them in the chat. And again, do not hesitate to write your questions anytime in the chat in French or in English. We'll try to answer most of the questions after this presentation. So in the following, I will present these different passive seismic methods. There are other methods, but these are the most common ones. So I'll cite them. The H/V spectral ratio, refraction microtremor, spatial autocorrelation, and we'll focus a bit more on passive tomography from seismic interferometry only because it's a new method and it's less known in applied geophysics. So again, the aim is not to describe in details each method and its theory, but to present it briefly and present the differences, focus on the differences between these different methods. So we'll start with the H/V spectral ratio, or sometimes called HVSR. It's a method that exists since the 70s. And one measurement of H/V requires the use of only one three-component sensor with continuous recording of about a few minutes of ambient noise. And then the H/V measurement is obtained from computing the ratio between the Fourier amplitude spectra of the horizontal and vertical component of noise. So the result is an H/V curve that shows peaks of frequency, as you see here, These resonance frequencies are then associated with impedance contrasts in the soil. And using this simple formula and having the average velocity in the medium, we could compute the depth of these contrast or a strong impedance contrast in the soil. So this simple method can be used for a rapid site characterization and mainly for detecting strong impedance contrasts such as the bedrock depth. If we consider this seismic network with 16 sensors, so a very simple seismic network, just for the sake of comparison, the result of the H/V method would be a 1D measurement corresponding to a depth value at each sensor. So here, for example, we could have 16 depth values measurements. And to obtain, let's say, a 2D model, we could by interpolating these 1D results. The horizontal resolution, for example, would be equal to the distance between the sensors. And when it comes to reliability, it's definitely not the most reliable method, but it's a simple and fast one. Here's an example here of a 3D H/V result obtained from 33 sensors, here presented in red triangles. The measurements are depth values of the bedrock, and the thickness of the layer that we see here in gray is related to the uncertainty on the measurement. We actually computed the depth using a range of velocities. Another method is the REMI, or refraction microtremor. So this method is similar to the MASW, multi-channel analysis of surface waves method. It requires a linear array of 1C or 3C, so one component or three component sensors. But instead of using an active source signal, we record seismic noise for a few minutes. Then using the FK method, dispersion curves of surface waves are computed and then inverted in 1D shear velocity models. So the aim in general is to have a rapid characterization of the subsoil from shear velocity 1D measurements. But a very important condition for the application of this method is the incidence of the noise signal that should be either homogeneous in the medium, which means a noise that comes from all angles, either coming from the sides of the array. Because if the noise signal comes from another angle, the velocity measurements will be wrong. So that's very important information, and sometimes, unfortunately, it's not taken into consideration. So if you consider now the same network of 16 sensors with the REMI method, we could have between 4 and maximum 16 measurements, corresponding to the number of arrays of sensors that we could consider. From each array, we obtain a 1D measurement averaged along the array, and the resolution of one measurement is related to the length of the array. And again, we could have a 3D velocity model with this method from interpolating 1D models. In this case, the resolution would be related to the length of the array and the distance between the different arrays. Here's an example of a 3D model of shear velocity obtained from REMI method. So here, 5 profiles were deployed, and each profile was divided by 5 sections. On each section, the REMI was applied. So this 3D model here is obtained from 25 interpolated 1D shear velocity models. The resolution depends again on the length of the section and the distance between the different sections. So for this study to be reliable, again, I insist on this point, the incidence of the noise should be analyzed and it should be homogeneous in order to be able to use these profiles that have different orientations. Now, another method is the Spec, or spatial autocorrelation. The Spec requires a 2D array of one component or three component sensors. 2D means sensors placed on a circular or triangular array in order to cover all azimuthal angles. And it requires recordings of a few minutes as well of ambient noise. The procedure is similar to the REMI or MASW, but the dispersion curve is computed differently. It is obtained from the spatial correlation coefficient. This method is also applied for rapid site characterization from shear velocity. And again, if we get back to the same network of 16 sensors for comparison, we would have 4 measurements with the Spec method, since we have to consider 2D arrays with sensors that cover all the angles. And the 1D velocity model would be averaged for one array. The resolution is again related to the dimension of one array and the distance between the 4 arrays. And here is an example of the Spec method in 3D. For this example, 49 sensors are placed on a green patch here and then shifted 3 times. So measurements were done 1 time by patch. On each patch, the Spec is applied on a group of sensors centered with 1, so a small square of 9 sensors. And in total, for this area, we got 100 interpolated 1D VS models to obtain this 3D model. The horizontal resolution is equal to 2 times the inter-sensor distance, which is the dimension of a small patch. Now, the last method that I'll present today, and which will be our focus, is the 3D tomography by seismic interferometry. The use of ambient noise and the technique of interferometry exists since, let's say, around the 70s. But it's only around 2004, 2005 that seismic interferometry was applied to ambient seismic noise, and it was a major progress in seismology. So this method is not, the theory is not new, but it's recently applied in seismology and very, very recently applied in applied geophysics. So for this method, we need a 2D network of either 1 component or 3 component sensors and a much longer duration of recording. So here we talk about few days or even longer, depends on the area. And the result would be a 3D velocity model, as we see here, with relatively high precision and a 3D characterization of the site with a relatively high resolution. So the procedure, again, is very similar to the MASW. From noise data, we apply a mathematical procedure that is the seismic interferometry that allows the extraction of surface waves. Then we compute a dispersion curve, we invert them into VS models, and then obtain the 3D velocity model. So the method sounds simple, but it has some challenges. So in order to present to you this method, I will show you step by step how it is done, starting with the acquisition. So the acquisition consists of deploying a network of sensors with very random design. So the sensors are small autonomous nodes, as this example here. And here are 2 maps of 2 examples of projects that we worked on. The sites were in urban areas with dimensions of few hundreds of meters. And we deployed networks of here, for example, 80 sensors and here 230 sensors. And this is just to show the order of magnitude of an urban project. And here, in both cases, The aim was to image the subsoil down to about 70, 80 meters maximum. So in both cases, by the way, the aim was to image the soil along the future route of a tunnelier. So the sensors, as we see here, follow the route, the future route of the tunnelier in yellow. Here I show you an example of a noise data for one sensor and only the vertical component. And this is a recording for about 3 weeks. We see clearly the difference in the amplitude of the signal between day and night and between weekends and during the week. And this is a proof that the noise sources are mainly anthropogenic. And here we have the noise signal spectrum, so the amplitude as a function of the frequency. And as we see, it covers a large range of frequencies. So this signal would allow to image the subsoil at a large range of depth. So here it goes from 1 Hertz to 100 Hertz, for example. Now, how do we go from noise signal to a dispersion curve? So the procedure is called Seismic Interferometry, and it consists of computing the cross-correlation of noise signal between two different sensors. So in theory, with the cross-correlation, if we have the right conditions, such as a homogeneous distribution of sources, we could obtain what we call the Green's function, which represents the impulse response of the medium between two sensors. If I want to explain the cross-correlation procedure in a very simple way, it is a function that computes the similarities in the signals at two sensors, so it allows to extract the waves that are hidden in the noise signal and that propagate between these two sensors. So the cross-correlation signal would look like that, centered in 0. The positive part would be equivalent to a surface wave emitted by sensor 1 and recorded at sensor 2. And the negative part is the opposite. It's a surface wave. It's equivalent to a surface wave emitted by sensor 2 and recorded at sensor 1. So if we extract the surface wave that propagates between the two sensors, and if we measure the propagation time from sensor 1 to sensor 2, and knowing the distance between these two sensors, we could measure the velocity of the wave that propagates between these two sensors. And this is how we obtain velocity measurements between pairs of sensors. If we get back to the same array of 16 sensors, with which we have maximum 16 measurements with the other cited methods, here we could have 136 measurements with the seismic interferometry method. Why? Because simply we compute cross-correlations between each two receivers. So we have one measurement by pair, and with 16 sensors, we could have 136 pairs of receivers. So the result would be a 3D shear velocity model, and the resolution is equal to the distance between sensors, because you have one measurement between the area in the area between two sensors. And the reliability, well, it's difficult to give a number or precise number, but compared to the other methods, it's relatively high only if we consider the high number of measurements. Okay, so now with a typical project, as this one here, with 80 sensors, we have more than 3,000 measurements, equivalent to 3,000 pairs of receivers. And by the way, with such a network, we could have 80 measurements maximum with the other methods that were cited earlier. So imagine the difference in the number of measurements, and this is what makes this method reliable, or more reliable, let's say, and allows a precise imaging of the subsoil. So for this project, by the way, we used only vertical sensors. So we analyzed only the Rayleigh waves, but we could use three component sensors and invert at the same time Rayleigh and Love waves. Okay, so here is the final result. Again, the aim of this project was to analyze the subsoil down to about, let's say, 60 meters along the future route of a TBM, tunnelier, and to detect major heterogeneities in the medium. So here is the final 3D shear velocity model. The color range represents the values of the velocity in the area of study. And we use this visualization software that we developed to visualize the results and extract I don't know, sections, observe the results, the velocity change in the volume, etc. So in this area of study, we were able, as you could see here, we were able to detect the different seismic horizons and a low velocity zone that corresponds to a passage of clay, the layer that we see here in red. And we were able also to observe and measure and observe the velocity variations along the future passage of the TBM, in which we see large heterogeneities. So we suppose that the path of the future TBM crosses the layer of clay that we see here in red and yellow. And well, I could tell you that these results were very helpful for a better adaptation of the TBM digging parameters. Okay. I would like to show you another project that we worked on. This one was in an area where the TBM has already passed, and the aim was to analyze the subsoil to study the impact after the passage of the TBM and to highlight the areas where the soil was weakened and presents a risk of collapse or, for example, etc. And that because there was a planned soil improvement project with a resin injection, and the 3D analysis of the subsoil helped target better these injections. Okay, so I presented to you a few passive seismic methods and their main differences in terms of resolution, form of results, reliability, etc. But the choice of the method depends on what we are looking for. So are we looking for an average characterization of the subsoil? Are we looking to have an estimation of the velocity in the first 30 meters? Are we searching for the bedrock depth? Or do we need to have detailed characterization of the subsoil, detect lateral heterogeneities with high resolution, image the subsoil from surface to larger depth? So a very important question as well is, what are our resources in terms of budget and time? For example, the 3D tomography from Seismic Interferometry definitely requires more time for the data mining, since we deal with a larger number of measurements and a big quantity of data. So, but of course, the result is much richer. So, the design of the solution depends on all of these parameters. There are also the conditions of the area of study that should be taken into consideration, such as the topography, etc. So all of these parameters are important in order to choose well the method that is adapted to the project. And for that, we are here to guide you and follow you through your project. So thank you, and to you, Simon.
Okay, thanks. So I think we have finished. It's over for this part. Maybe you can put the other slide. Yes, perfect. So first, thank you all. If you have any question, as I said before, you can write it in the chat, or you can send us an email or contact us by our cell phone number. Here I see in the chat two first questions. I think the first one is for you, Maria. So what is the impact of the type of noise sources around the study area? For example, if I am in a rural area, will it affect my model, and to what extent?
Okay. Are the type of the noise source Okay, so please correct me if I didn't understood well your question. So of course, the noise that we consider is noise that could be emitted by different type of sources. And if we are in an urban area, the amplitude of this noise would be much larger. So it would be much better for us. So well, the sources could be various. It could be any kind of human activity, a construction site, the cars, trains, etc. So we use all of this noise, and its amplitude could also define the time of the acquisition. For example, if we are in an urban area and the amplitude of noise is much more important, and there's much more sources, we could, for example, record ambient noise for less time. Let's say, I don't know, 2-3 days. Now, how does it impact our model? The amplitude should mainly define the time of the acquisition, and it could improve the signal to noise ratio of the cross correlations. But the more noise, the better. That's all I could say. So if I did not answer your question, please do not hesitate.
Yeah. I think Cyril has the same question, why we need many days of data.
Yeah.
So I think it's an answer. Maybe.
Yeah. Well, actually, we compute cross correlation for small sections of time, and then we stack. It's like we compute the average of the cross correlation for a larger time to improve the signal to noise ratio of the cross correlation and to extract better the surface wave from these cross correlations.
Ivan asks us, for the ambient noise tomography, what are the longer periods where you can recover with 1C geophones?
For the ambient noise, the longer period you can recover with, maybe you mean the shorter period? Because the longer, the better. The more we have data, the better it is. Now we could, depends on the area of study. Sometimes we could have enough signal with a few days, 2-3 days. Sometimes we need 2-3 weeks of data. So it all depends on the amplitude of the sources. Now the 1C geophones that we use have a battery of 2-3 months maximum. So this also is an important parameter.
Okay. If I think the next one I'm able to answer. If we compare the result of the VS model with the geotechnical parameters, we have this question by Clement and Cyril. Clearly, we do that with the geotechnical engineers on the project of TBM, and most of the time it was very accurate, notably for the speed, the excavation rate exactly of the TBM. We can compare this rate before going to the clay layer and after, and clearly there is a huge difference. It's not 2 times more, but it's a big improvement. And so for the planning, it's very, very important to know that for a TBM driver. I think I will answer. Jeremy asks us, regarding interferometry, how do you get your VS value from the cross correlation? Does it one from the Isaac algorithm?
Well, it's a very simple procedure, even simpler than the MASW. It doesn't even require an FK computation. It's very simple. We compute the delta T of the propagation time. So we extract the wave from the cross correlation that is equivalent to the source, the surface waves that propagates from one sensor to another. So from the delta T, knowing the distance between the sensors, we compute the group velocity actually of the wave propagating from one sensor to the other.
Okay. Cyril asks us, but with a simple VS log profile. I'm not sure to understand your question, Cyril. Can you, maybe you can turn off your mic?
Yes, my question is just to compare VS profile with a simple downhole or one log.
In few projects, we make the 3D model is fixed by parameters of layers or range of velocity. So in few surveys, we have the chance to have a downhole or a crosshole acquisition right next to the area of measurement. So clearly it's better to do that if you want to compare the VS model with the real measurements in situ. But most of the time, I only have geotechnical drillings, you know, like, but most of the time it's enough to have a proper result, you know, to fix the depth of the layers, the thickness of these layers. So it depends on the site and the precision, the resolution you want on your survey. But clearly, it's better if you have a downhole on a crosshole acquisition. Another question, if you don't mind, for the ambient noise tomography, do you recommend any array geometry of sensor in order to maximize the resolution of the tomograms?
Okay, so we could tell you briefly how we designed the geometry. So first of all, we define the dimension of the geometry depending on the depth that we need to image. Just to have an order of magnitude, the dimension should be about 6 times the depth that we need to image. And then we define the distance between the sensors depending on the resolution that the horizontal resolution, lateral resolution that we would like to have. And then the design should not be regular. It's not that it should not, but it does not have to be regular. And if it's messy, if I could say that, it would be better. And sometimes also the area where we're deploying the geophones decides for us where we could deploy them.
Clearly. Fanny, how much time for study the measurement data? For example, 80 sensors, as you see in the presentation. If I could remember, it depends a lot of your informatic resources, but with some cloud computing, you can hope something like 2 to 3 weeks to obtain a 3D model, something like this. But it depends a lot of your informatic resources on this. All right. So, what about your uncertainties when computing the final model? And did you get good results in case of velocity inversions? What is your usual sensors frequency band?
Okay, usual sensors frequency band. Well, we have sensors with a cutoff frequency of about 5 Hertz. We could extract frequencies a bit down to 1 Hertz, and we use we have data to about 250 Hertz, but then we extract data from the dispersion curves generally to around, let's say, 30, 40 Hertz. So in general, we work between, let's say, 1-2 Hertz and 30, 40 Hertz. Now,
and the big question of uncertainties.
Yeah, uncertainties are, it's difficult to give a number, but we could have, for example, misfit, the misfit of the inversion, a step at the end. So, and usually we have like a misfit of maximum, I would say 20%, not maximum, average of 15%. But if I could add also, excuse me, this misfit or the error that we could have on the data generally does not change the interpretation. So it does not change drastically the values of the velocity and the global 3D model.
Okay, did you get good result in case of velocity inversions?
Oh, I think I did answer this question.
And maybe you can show the 3D model. Yes, here.
Yeah, as I said earlier, we have a misfit of about, for this project, it was an average of about 8%, if I remember well, for all of the measurements in each grid. And again, it does not change the interpretation. 8% error, let's say, on the velocity measurements, that would not change the interpretation of the measurement.
Okay, another question from Ivan. Last question for me. For the dispersion curves, did you pick manually the curves, or did you use some automatic picking software?
If you have a solution to pick manually more than 3,000 measurements, I would be glad. It's impossible. So we compute, we extract as much as possible dispersion curves. We extract different examples in the whole area to analyze them, to check if there are where we see the fundamental mode, if there are higher modes, etc. But then we program this picking automatically, of course, after the after analyzing different examples and defining the ranges of frequency, the ranges of velocity, etc.
Okay, so I think we answer all questions, or maybe I don't know. Any last question for someone?
Anyway, you have our contact. You could contact us.
Put the slide with the contact. Just okay. And are you able to distinguish higher modes with your methods? Do we use higher modes?
We do not use higher modes. We only invert the fundamental mode of Rayleigh wave, and in case you have 3C sensors, we invert. We have a joint inversion of fundamental mode of Rayleigh and Love waves. We do not invert higher modes, but of course we observe them sometimes, and we try to, of course, we try not to point them in the picking of the dispersion curves.
Okay. Well, I think we can say it's over for this talk. I like the comment of Ivan. Thank you all to be here. Very pleased to see you there. If you have other question, you can send us an email or a phone call. It will be with pleasure to answer you. And it's time for us to see you. Bye-bye.
Ciao, bye-bye.
Thank you very much. Bye. Very nice.
Thanks.
Thank you.
Bye.
Bye-bye.
Bye.